All right, class, welcome to section 1.3. So we will continue our discussion on derivatives. It's really important, as I said in the first video, we're going to be talking about derivatives for the first 4 chapters. In other words, the very vast majority of this class, okay? And we're going to start seeing some of the applications of derivatives in business today. So as you saw in the first 2 sections, actually in 1.2 is when we first talked about derivatives, the process of finding a derivative seems to be quite long. And it involves a lot of algebra, manipulation of expressions. So since it's such an important topic and it seems like we're gonna have to be finding a lot of derivatives, would it not be great to have a shorter process to finding that? So that's exactly what we're starting now. So we will simply start developing some formulas to find derivatives rather than go through the long limit definition of a derivative. So we're going to start with super simple functions. Okay, so yeah, I was giving you guys here an example if we could develop some formulas to follow, and even though you might not like formulas quite as much, but the quadratic formula you guys have learned in algebra definitely pays off, because now every time you want to solve a quadratic equation, you get to use the quadratic formula, okay? So before that, yes, it was factoring, but only very few quadratic expressions are factorable, so you would have had to do the completing the square method every single time, right, if it wasn't for the quadratic formula, okay? So let's see how the formulas of derivatives will apply, okay, and how much easier that is. Okay, so we're going to start with constant functions. What is a constant function? Is a function that doesn't change one bit. So in other words, f of x is equal to 3, for example, right? That's a constant function. What does the graph of a constant function look like, if you remember? If you were to graph y equals to 3, where f of x equals to 3, I remember that that's simply a horizontal line that crosses the y-axis at 3, right? So it's constant, it doesn't change no matter what the x values are, yes? The y always stays to equal to 3, yes? Okay, so the derivative of a constant function, it's super easy to find. It's always 0. So the derivative with respect to x of any constant k is equal to 0. I'll write this down. The derivative of a constant is 0. What does that mean? As you see, what does the derivative mean? It's the slope of the tangent line, yes? So if you pick any point on this line and you want to draw the tangent line to the graph, a tangent line is a line that's going to touch it, yeah, not cross it, okay? So as you see, any tangent line to a line itself is the line itself. So what's the slope of a horizontal line? The slope of a horizontal line is 0, right? So the slopes of all these tangent lines are 0, okay? So what we're simply saying is that k, because it doesn't depend on x, right? It doesn't have an x in it, there's no change in it, right? X has no bearing, is not changing at all, these y values, okay? So there's no change in y's, okay? A linear function, as we saw last time, and we drew this same 2x plus 3 function, linear function. I'm going to draw it one more time for you. So 2x plus 3, 3 is the y-axis intercept. The slope is 2 over 1, so here it is. Yes, we drew this already. What will be the slope of any tangent line to it? Well, there's a point. Here's the tangent line to it. Here's the point. Here's the tangent line to it. Yes. So any tangent line, again, to a line is the line itself, okay? So what's the slope? Remember, the derivative is the slope of the tangent line. So what are the slopes of these tangent lines? Well, it's the same as the slope of the line itself, right, which is 2. So the derivative If you write it in red, keep it consistent. Of any linear function is equal to its slope. Okay. All right. So, in other words, the derivative, and I'm using the Leibniz notation that we talked about last time, of any linear function of the form y equals mx plus b, right? So mx plus b is just the slope itself, right? So it's going to be m. All right. Now, specifically, this is one that we will be using mostly. If you have the linear function that says y equals to x, or we also call this the identity function. Why? Because y is always equal to x. Okay. So sure enough, the y-intercept for this line is 0. What's the slope of this line? Well, it's 1. So y equals to x, we also call this the first bisector line, because it bisects, in other words, cuts in half the first quadrant. Okay, so the derivative of x with respect to x is equal to 1. So really, it's just, this is what I have, dx over dx. Yes, if I put this x up at the top, and as you see, that definitely equals to 1, right? So that Leibniz notation is helping us in this sense as well. Again, what is a derivative? It's a change in y's with respect to change in x's. But if y's are the same thing as the x itself, yes, then of course y's are changing the same thing the same way as the x's, right? So that ratio is going to equal to 1. Okay. All right. Let's continue. Now, we would definitely want to extend that to higher powers than 1. So I want to look at x squared, x cubed, and so on and so on. So this is what a power function is. Not x to the 1 is one of them, but x to the 2, to the 3, to the 4, and so on and so on, okay? So it's not going to look good if I'm trying to graph these functions. So here it is. I'm just going to try and graph the cubic function for you, just to show you that it's not as easy as what we were able to see with the linear functions. When you graph a cubic function, if you remember from your algebra classes, it's going to look somewhat like this. So what about the derivatives to the graph? Well, as you see, these tangent lines are definitely changing very much, right? So they don't look like they have the same slope as in a linear function. So we can't just say, oh, it's the same as what, right? So no such thing. So the power rule is the most powerful of all the formulas we are going to learn. So I'm just going to write it down here. So the derivative with respect to x of x to any power n is going to equal to n times x to the n minus 1. There's your rule. So what we are going to do, and again, this is going to be the most helpful formula that you will learn this semester, really, if anything. That's the one that we're going to be using mostly. So again, what we're going to do is, according to this formula, is we're going to take the exponent up front and then multiply it to an x, and what we're doing is we are decreasing that exponent by 1. Okay. So written, if you want, as a, I'll put it in with the Newton notation, right, with the prime notation. So the derivative of x to the n is n times x to the n minus 1. So let's see, for example, just a couple of them, okay? So what's going to be the derivative of x to the third? So that's one way of writing it simply, yes? So the derivative of x to the third, according to this rule, is we're going to take the 3 up front, multiply by an x to the, decrease this exponent by 1. So it's 3 times x squared. Just as easy. What's the derivative of x? Well, we already learned that the derivative of x is 1. So let's see, how does the power rule that deals with x's to any power in general, and again, this might look like a 1, but it's a prime. So I'm just going to fill in this 1 power here. So according to the power rule, what do? I take that 1 up front. X to the, what do I do with this power? Decrease it by 1. So 1 minus 1 is 0. Now, of course, you will have to remember that anything raised to the power of 0 is equal to 1. So just as we have already shown or looked at on the page before, the derivative of x is equal to 1, right? So this power rule also proves it. Okay, so we call this one more time the power rule. I'm going to review them all for you on the next page. Okay. All right. Constant product rule. What does that mean? So what we want to do is basically we want to extend these formulas to polynomial functions. So fine, I know what to do with the number only, right? The derivative of 3 is 0, right? I know what to do with x's with certain powers to them. So now I want to see what happens if I multiply 3, a number, a constant, to an x to some kind of power or some kind of expression with x. So here it is. If you have a constant times a function, right? It could be an x to the third. It could be something complete. We're going to make it more and more complicated as the semester goes on. And you want to take the derivative of this. What's going to happen is you're going to keep that constant and move on and take the derivative of the function itself. So I'm going to put this in Leibniz notation as well. Maybe that looks better. So in Leibniz notation, the derivative of what? A constant, a number that has nothing to do with x, right? Times some kind of function of x. What we do is we keep the constant and then just move on and take the derivative of the variable part. Okay, so I'm going to write this down. So keep the constant factor. We call this the coefficient also. Remember, if you have, let's say, like a 3x cubed, or let's say 3x to the fourth, the 3 is called the coefficient, right, of this. It is a constant factor, but when it's multiplied to a variable part, we call that the coefficient of that variable, right? So keep the constant factor, and I'm going to say then next, times the derivative of the variable part. So what I'm going to do right away is I'm going to take the derivative of this term right here. So let's say here's my function, right, that says f of x is 3x to the fourth. What's going to be the derivative of this function? Now, as you see, you have a coefficient, right, or a constant factor. So the derivative, this rule here says I'm going to keep that coefficient, right, the constant factor, times, move on and just take the derivative of the variable part. For this part here, we're simply going to use the power rule, right, from up above. So what's the derivative of x to the fourth? Well, the power rule says you bring down the exponent times, you decrease the exponent by 1. So 4 minus 1 is 3. So the answer for that would be a 12x to the third. Okay, you will be able to do this super fast with more and more practice. Again, what we're doing is we're keeping this 3, the 4 comes down and multiplies to this 3, and then I decrease the power by 1. So you'll be able to do this just as easy as 3 times 4 is 12, x to the third. Okay. And again, just a little practice. It's not a complicated rule. Okay, and the last rule for today is the sum difference rules. What do I mean by, again, I want to now be able to do what? Take a term like this, it may be added to an x squared, and then added to a 5x, and then added to something else. So I want to extend this to more and more terms. I want to turn just one term into a polynomial, right? It will be able to actually take derivatives of more than just polynomials today. So, sum and difference rule says simply this. If you want to take the derivative of a sum or a difference, it's as simple as what? Take the derivative of each one of the terms and move on, plus, minus, whatever it says, take the derivative of the next term. Okay, just as simple as that. So in other words, you simply go term by term, you distribute that. So I'm going to write this down, and again, I can put this, I'll put it on the next page. So I'm just going to write this. When taking derivatives of sums or differences, okay, simply take the derivative of each term. Okay, so you go term by term, move on. That's it. So let's just keep something super easy that we already know how to deal with. So what would be if, let's say I'm giving you a function f of x that says x plus 5. What's going to be the derivative of this function? So the derivative of this function, see how it's made up of 2 terms? Okay, and we go term by term. Do you remember what's the derivative? So we'll just simply take the derivative of x plus the derivative of 5. What's the derivative of x? We just went over that rule. The derivative of x is 1, yes. Last rule on the previous page. Plus, what's the derivative of a constant, right? It doesn't have any x to it. It's just a 5. There's no variable in it. So the derivative of any constant is 0. So 1 plus 0 is going to equal to 1. So this is how, and we're going to extend this to more complicated terms in just a bit, but this is simply how you go term by term. Okay. So here is a review of it all. We're just going to put it a little bit together. I just wanted to give you a look of all the rules that we've been talking about, and there they are. So the derivative of a constant, yes. In other words, see how there's no x in it, right? It's just a constant. Okay, and of course, if your variable should be called z or a or t, then there's no z or a or t in this constant there. So the derivative of a constant is 0. Constant multiple rule. I should say this one was our next one. So to put it up above, the derivative of x is 1. Yes, so dx over dx, that's just 1. Constant multiple rule says the derivative of a constant times a function, which again, that's its notation in Leibniz notation. We do is we keep the constant and just move on and take the derivative of the function itself, right? So just keep the constant and move on to the variable part. Sum or difference rules, right? Again, written in the 2 form, Leibniz notation and, Leibniz notation, and that's the Newton notation. So simply says that what? The derivative of a sum or a difference, you move on and you take the derivative of the first term, plus or minus whatever it says, take the derivative of the next term. And sure enough, we don't just have to have 2 things added together, right? If there's more terms, we're just going to be going on through each one of them, okay? And the power rule is the most important one. That simply says the derivative of an x to any power, you take down the power, and then you decrease that exponent by 1. Okay? All right. So here are the rules. We're going to be using them so many times throughout the semester for different reasons. We're going to extend and make things more complicated, of course, but these are at the base of it all, or the most basic rules, I should say. Okay, now we're going to jump right in and take a whole bunch of derivatives next, but what I want to show you is that we can extend the power rule to other expressions that might not necessarily look like the power rule to you. So, rationals. You have learned that if you see a fraction with an x in the denominator, right, what does that really mean? We could rewrite this fraction, yes, as an x to a negative n. So in other words, let me just rewrite this. What is 1 over x squared? Well, you've learned in algebra that this is nothing but x to a power of negative 2. So now all of a sudden we have extended the power rule to fractions. Now, there is no rule in here that says how we're going to be dealing with fractions. The only thing, again, that's coming up in a couple sections, and I'm promising you that what we will call the quotient rule is going to look very complicated. It's not easy. So, however, if you have a simple 1 over something, then based on algebra, we can take that denominator to the top, right? Just promise to change the sign of its exponent, right? So x to a negative exponent means 1 over x to that positive exponent. Of course, if you have a minus here, then it turns into a plus up here. So it's the opposite, yes? So what is, for example, 1 over x to the 5th? That's the same thing as an x to the what? Negative 5. We're going to extend this and make it a little bit more fancy in just a bit. What is 3 over x to the 7? What if you have a 3 up here and not a 1? Well, 3 is 3 times 1, so all you do is you keep that 3, right? This is the same thing as 3 times 1 over x to the 7, but the point is this x to the 7 is simply going to come up at the top next to whatever is waiting there for him, right? Whether it's a 1, which I don't have to write in a product, or some other coefficient or constant. So that's going to be a 3x to the negative 7. And we definitely have already what we call a what? Constant multiple rule, right? What do we do with the coefficient basically? And the power rule. So we'll be able to take the derivative of such a fraction in the end. Okay. The other really important one is radicals. Now, if you remember from algebra classes, radicals are nothing other than what we call rational exponents. So radicals are rational exponents. Rational means fractional, right? So I'm going to say this: fractions are negative exponents. Squished it in there. Okay, so just let's review. You've learned basically that a square root of x can be rewritten. So all of a sudden, we will be able to take derivatives, not just of nice polynomial, x to the 3rd, x to the 5th, but fractions and radicals. Why? Because a square root of x, you have learned, is the same thing as an x to the power of 1/2. Why 1/2? This rule here says, right here, that what are you going to do? The index of the radical is your denominator, yes? If this x should come to some power, that's your new numerator, okay? So what's the power of this x? It's 1, yes? So that's why that's your numerator. what's the index, we call it, of this radical? If none is written, it always means a 2. So that's why that's an x to the 1/2. How else could we rewrite a cube root of x? All right, a cube root of x as an exponent, right? There's an x to the what exponent? Again, this x comes to the 1, so it's a 1 divided by 3. How would you rewrite a 5th root of x to the 3rd? Well, that's an x to the what? 3 over 5. In this order. A common mistake for students is to go 5/3 because you see 5 first, but it's not. This is the denominator, okay? Now, very well, let's try this fancy one. Let's put a 3 here too. How would I rewrite that? Well, first of all, this is a 1 over. How do I rewrite this part here? This is an x to the power of 3/4, yes? It's still a fraction. How do I eliminate, let's say, this fraction? So comma from above. I eliminate this fraction. How do I bring this x up at the top so it wouldn't be a fraction anymore? It's an x to the -3/4, right? So we're combining basically both these rules. If you have a fraction, that means that's coming really from a negative exponent, right? You just put it back at the top, and then it's not a fraction anymore, right? So you just take the opposite of this exponent. And then if you should happen to have a radical, then that's a fractional exponent, right? The index of the radical is your denominator. If this should have an exponent here, then that's your numerator. If there is no exponent, that always means a 1, right? All right, so we're gonna finish this video here, and we're gonna get on to taking a whole bunch of derivatives super fast without that limit definition.